Hi everyone, I am here once again, Dr. Divya Bartaria from United Group of Institutions, Allahabad, with the fourth lecture and the last lecture related to covalent bonding, chemical bonding in fact, and today the topic is band theory of metals. So welcome to this fourth session of chemical bonding, in which we will discuss the band theory of metals. Now assuming that you have studied the theories of metallic bonding, we will discuss in brief the concept and theories of metallic bonding before coming to the main topic, which is the band theory. On the basis of band theory, we will also classify the materials into different categories. Applying the theory over these materials, we will try to understand and define the characteristics of these three categories of materials. So let us come to the agenda first. Today, first of all, we will start with the metallic bonding. What do we mean by metallic bonding? What is the concept and what are the theories of metallic bonding? An overview will be there. Then we will study in detail band theory of metals. Application of band theory in explaining the conductance properties of conductors, semiconductors and insulators would be our last topic. So let us come to the first topic, which is metallic bonding. Now when we talk about the metallic bonding, the first and the instance idea comes into our mind that metals are characterized by their electropositive character. Electropositive character means metals have a tendency to lose electrons easily, right? So sodium is a metal, it has a tendency to lose electron easily. It has one electron which is released and it is converted into positively charged ion, that is cation. So this is the special feature characteristic of all the metals. Now these positively charged metal ions or cations are arranged together in many of the crystal structures which has 8-fold or 12-fold coordination. Now what do we mean by 8-fold or 12-fold coordination? This means that each metal atom is surrounded by 8 nearest neighboring atoms. For example, in case of BCC, body centered cubic unit cell, you can see that each metal atom or ion is surrounded by how many atoms? 8 nearest neighboring atoms. Similarly, if we talk about 12-fold coordination, then each metal atom is surrounded by 12 nearest neighboring atoms. Now the point of discussion is that the number of valence electrons is only 1 or 2. Even the valence shell orbitals is 3 only. If we consider the example of sodium, then there is only one valence electron and there are 3 valence electron shell orbitals. So the problem is that the number of valence electrons are not sufficient to hold these neighboring atoms together. So how do we account for bonding in metals? This is the question which has to be answered here. So metals are characterized by a special type of bond known as metallic bond. So how it can be defined? It can be defined as a bond which is formed between electropositive elements. As we have seen that if there is one electropositive element and the other is electronegative element, then which type of bond is formed? We consider the formation of ionic bond, right? Ionic bond. Similarly, if both the atoms are electronegative plus electronegative, so in general what we see that it is covalent bond, right? And similarly at the end, when we consider both the atoms to be positively charged ions, or even in a crystal lattice which we see that large number of positive ions are packed together in various crystalline forms, then the bond formed is a metallic bond, right? So this is how we have considered the second point, a bond which is formed between electropositive elements. So this is a kind of attractive force. So in the third point, a very general definition has been given, the attractive force which holds atoms of 2 or more metals together in a crystal lattice or an alloy. So this is a general concept or definition of metallic bonding. Now any successful theory, because various theories have been put forth in order to explain the nature of bonding in metals. So any successful theory is better to explain the nature of bonding in metals when it explains 2 important points. Number 1, non-directional nature of metallic bond. You can see here non-directional nature of metallic bond. What do we mean by directional nature or non-directional nature of metallic bond or bond? No, directional nature means we can consider the example of covalent bond. All covalent bonds are directional in nature. This means that they have specific geometry, definite geometry in three-dimensional space. But in case of ionic bond where charges are there, there is non-directional nature of bond. And in case of metals also we consider to be non-directional nature of metallic bond. So, any theory is successful when it is able to explain the non-directional nature of metallic bond, and the other important point is it is able to explain the delocalization and high mobility of electrons. So, keeping these two important points in mind, following three models have been proposed: free electron model, then another is resonance theory based on valence bond theory, and the last one is band theory of metals based on molecular orbital theory. If we consider free electron model, then it defines that the positively charged ions or kernels are immersed in a sea of electrons, right. So, there is delocalized electron. A sea of electrons is flowing all around the kernels, and that is why it gives a kind of explanation for the strength of the metallic bond. While in case of valence bond theory, valence bond approach is there, resonance is there. So, it is being considered here that the metallic bond has essentially covalent character, and because of resonance the strength of metallic bond could be explained. But lastly, band theory came, band theory of metals came. So, this theory is based on molecular orbital theory. So, today we will be focusing on the last theory, band theory of metals, which is based on molecular orbital theory. As we can see that we have started from molecular orbital theory, now it is an extension of molecular orbital theory. So, at a very first instance we can say that molecular orbital theory extended to solids is also referred to as band theory. So, remember that according to this theory, all the electrons of all the atoms in a metallic crystal belong to the crystal as a whole, and the metallic bonding results due to the delocalization of all the electrons over all the electron orbitals over all the atoms in a metallic structure. What does this mean? It gives us an indication that one single electron is not belonging to one atom, one or two atoms, but it is belonging to the entire crystal, and it shows, it explains the delocalization of all electrons, delocalization of free electron orbitals over all the atoms in a metal structure or an alloy. So, let us consider the formation of a crystal. We are going to consider the construction of a crystal of sodium atom, or even we will be considering here lithium atom by adding lithium atoms one at a time. So, suppose we are going to consider 2 lithium atoms, so we will get lithium 2. If we consider 3 lithium atoms, we will get lithium 3, lithium 4, lithium 5 and so on until we have lithium N. So, let us consider the formation of lithium crystal solid. So, if we consider lithium's electronic configuration is 1s2, 2s1, right. So, we are going to consider 2 lithium atoms and we will be considering only the outermost orbital, that is 2s1. So, suppose we are going to form Li2. So, in this case 2s1 and 2s1, 2 lithium atoms are there. So, by the overlapping of these two atomic orbitals, we will get bonding molecular orbital and anti-bonding molecular orbital. So, this is bonding molecular orbital and this is anti-bonding molecular orbital. So, total number of electrons is 1 only, so it will be here. If we consider 3 lithium atoms, so here we have to consider 2s1, 2s1 and 2s1. So, in this particular case we will get bonding, anti-bonding, and in between there is non-bonding. This is non-bonding. How many electrons are there? 3 electrons are there. These filling would be happening following the same rules of Bauer's principle, Pauli's exclusion principle and Hund's rule of maximum multiplicity. So, 1, 2 and 3. Similarly, Li4, Li5 and so on up to Lin. So, if we consider n number of lithium atoms, right. So, we will get a kind of band which is formed due to the merging or coalescing of all the molecular orbitals present in the molecule, in the crystal structure. So in this way it leads to the formation of energy band. This is the band which is actually responsible for various properties of metallic crystal. So if we are going to consider the lithium or the sodium crystal, we can see that N is the number of atoms of the order of 10 to the power 23, and that too in 1 centimeter cube of solid. So this number is very large, right? So as the number of atoms increases, the spacing between the energy levels of the various orbitals decreases further. Number of atoms increases and the spacing between the various orbitals decreases, molecular orbitals decreases. So it leads to the formation of energy bands. So what happens in general, n atomic orbitals may combine to form n by 2 bonding molecular orbitals and n by 2 anti-bonding molecular orbitals. For example, 2 atomic orbitals combine, then one is bonding and the other is anti-bonding. Similarly, if 3 atomic orbitals combine, then one is bonding, other is anti-bonding, and one left is non-bonding. If there are 4 atomic orbitals which are going to combine, that then n by 2 means 2 are bonding and 2 are anti-bonding, and so on. So this goes on. So in a metallic crystal there is a very large number of the order of 10 to the power 23. So these 10 to the power 23 atoms combine to form 10 to the power 23 molecular orbitals, and this is leading to the formation of energy bands of closely spaced molecular orbitals. Now there are some gaps. So the gaps between these energy bands represent the energies in which the electrons cannot be present. The gaps between the bands represent the energies where the electrons cannot be present. Therefore, these gaps are also known as forbidden zone or forbidden bands. Okay, so another important aspect is, if we have discussed the formation of bands, so let us understand that how it can be applied over different properties. So on the basis of molecular orbital theory or band theory, we can explain, not only we can explain the metallic properties such as electrical conductivity, thermal conductivity, etc., but also on the basis of this energy gap between the valence band, that is the completely filled band, and the empty conduction band, we can categorize the materials into 3 categories. The first one is true metals or conductors, the second one is insulators or non-conductors, and the third one is semiconductors, right. So this entirely depends upon the band gap, this forbidden zone or forbidden gap which is present between the valence band and the conduction band, right. So let us take it one by one. In case of true metals or conductors, what you can see here, there are basically 2 conditions. So before coming to the 2 conditions, we must understand that yes, true metals have excellent conductance. So what is the responsible factor for this excellent conductance? So first of all, the distinctive feature that we have to understand of a true metal is that there is either a partially filled energy band, right, or there is an occupied band overlapping an empty band, or in other words we can say that either there is a partially filled energy band or there is overlapping between the valence band and the conduction band. So if there is partially filled energy band, right, this is partially filled energy band. So here what will happen? So on application of potential difference, the electron will jump from the lower energy level to the higher energy level within the same band, right. So in this way the all the electron orbitals are delocalized, and we can easily explain the conductance, excellent conductance of true metals. Similarly, when there is overlapping between the valence band and the conduction band, again the situation becomes similar to this one. So in that way, on the application of potential difference to a true metal, the electrons in a partially filled energy band take up the extra energy and jump to a higher energy level of the same band. And since all of us know that these energy levels are delocalized, the energy, electrical energy, is easily conducted throughout the metal. Now what do we know about the temperature? If we increase the temperature, what will happen in case of true metals or conductors? Generally students get confused that as we increase the temperature, the conductance of the true metals or the conductors increases, but it is not like that. The conductance of metal decreases with an increase in temperature. Why? Because as the vibratory motion of atoms increases with temperature, this interferes with the free movement of electrons present in the true metals. So, the vibratory motion of atoms increases, free movement of electrons is hindered, and that is why the conductance decreases. So, in case of true metals, always remember that with the rise in temperature, the conductance or the electrical conductivity decreases. Coming to the next category of materials, this is non-conductor or insulator. Here you can see that in case of insulators or non-metallic elements, there is a big gap, there is a large band gap between the filled valence band and the empty conduction band. All low energy bands are completely occupied. This is the another important feature. All the low energy bands are completely occupied. There is no scope of jumping one electron from the lower energy level to the higher energy level, since all the lower energy bands are completely filled. So, electrons fail to conduct electricity as sufficient energy is not available to them to cross this forbidden zone and to jump in the next empty band of higher energy. And this is why we can explain the non-conductance of insulators or non-conductors. Semiconductors. In case of semiconductors, we know that their electrical properties lie between that of insulators and good conductors, right. So, in semiconductors, the specific feature is that the energy gap between the valence band and the conduction band is less than 3 electron volts. Therefore, less energy is required to promote the valence band electron to the conduction band. Now, it is very much obvious that the number of electrons promoted to conduction band increases with the rise in temperature, right. So, the conductance of the semiconductors increases with temperature. In case of non-conductors, there is no impact, no effect of increase in temperature. In case of metals or true conductors, true metals or conductors, the conductance decreases, while in case of semiconductors, since the number of electrons promoted to the higher energy level band increases, therefore, because of this small gap, the forbidden zone, the conductance of semiconductor increases with the temperature. Also, we remember the fact that the conductivity of semiconductors can also be improved by doping, and that is why we call it as extrinsic semiconductors. So, this is how we have categorized the materials into 3 categories, and how we can see that this band theory of metals is very much important in explaining the conductance properties of these categories of materials. Now, the question is, which of the following is a non-directional bond? Metallic bond, covalent bond and coordinate bond. So, as in the previous slides, when we started the session, I told you that all the covalent bonds and coordinate bonds are directional in nature because they have fixed geometries in 3-dimensional space, while this is not applicable to any ionic bond or metallic bond. So, these ionic bonds and metallic bonds are always non-directional in nature. So, amongst 3, metallic bond, covalent bond and coordinate bond, metallic bond is non-directional bond. Similarly, another question is, metals are malleable and ductile, why? So, we can very easily explain that because of the non-directional nature of the metallic bond. We know that the metallic bonds are having non-directional nature, and also they have highly delocalized electrons, mobile electrons. So, because of these 2 properties, we can easily explain the malleability and ductility of metals. And last but not the least, the last question is, what is the effect of temperature on conductivity of metals? That we have already understood that it decreases with the rise in temperature. So, friends and dear students, under the course content of chemical bonding, when we consider the overall content of chemical bonding, we know that we have discussed molecular orbital theory, we have discussed LCAO method, we have discussed the formation of bonding and anti-bonding molecular orbitals. Also, we have drawn the molecular orbital diagrams, we have written the electronic configurations of various homo and heteronuclear diatomic molecules. We have tried to calculate the bond orders and predict the stability and magnetic character of molecular and ionic species with the help of this bond order. And in today's session of chemical bonding, we have tried to understand the metallic bonding, in short, band theory in metals and its applications. So, this is all about chemical bonding. Thank you so much, and we wish to see you once again in another session of solid state analysis. Till then, I request all the students to go ahead and study chemical bonding. If you have any question, any query, do write to me. at 962882939, and this is my mail ID. You can note down my mail ID, and definitely we can come up with more ideas, more good lectures. Thank you very much.